This video is going to be a quick lecture focusing on examples of drawing disubstituted cyclohexane rings. Earlier in the semester, when we learned about drawing cycloalkane rings, we saw that we could use the terms cis or trans in order to describe the orientation of two substituents on a ring. If both of the substituents were either face up or face down, we use the term cis. If one substituent was pointing up and the other one was pointing down, the orientation would be trans because the two groups would be opposite of one another. When we drew our simple cycloalkane rings using cis or trans, we could also use wedged and dashed lines to show if a group was pointing up or pointing down from a ring. The ring was imagined to be lying in the plane of the paper. A wedged line meant that the group was coming out of the page, or in other words, pointing up. A dashed line meant that the group was going back into the page or pointing down. If we were to draw trans 1,2-dimethyl cyclopentane, we would first draw a cyclopentane ring, which would be a 5-membered ring. And then at positions 1 and 2, we have two methyl groups. And the trans tells us that one is pointing up and one is pointing down. So we would have one on a wedge and one on a dash for each of our methyl groups. If we were to draw the same structure but change it to cis 1,2-dimethyl cyclopentane, we could simply draw a 5-membered ring, and in this case we could have both of them on wedges or both of them on dashes to show that they're on the same face. So here I put both of my methyl groups on wedges. Of all the cycloalkanes, we're going to focus on cyclohexane. Cyclohexane can adopt a few conformations, but the most stable conformation is called the chair conformation. And we saw on the board that groups could either be in the equatorial positions or in the axial positions. Axial positions undergo 1,3 diaxial interactions, and therefore they're less favored or higher in energy. Equatorial positions are considered more stable because they do not undergo those 1,3 diaxial interactions and are in the equator of the ring. You want to be able to practice drawing cyclohexane rings in their chair conformation and being able to draw the ring flip that it will undergo at room temperature. Once we draw both of our conformations, we can identify the most stable cyclohexane ring conformation. Next, we are going to do a few example problems, drawing our molecules in that ring structure, drawing the ring flip, and identifying the most stable conformation. We have trans 1-bromo 2-methyl cyclohexane. First, it's helpful to draw our cyclohexane ring in a simple conformation. So we have just our flat cyclohexane ring. At position number 1, we have a bromo group. And at position number 2, we have a methyl group. And we know that those two are going to be trans, so one face up, one face down. Now draw our sketch of our outline for our chair. From here, we're going to place our groups. If you recall, the common numbering scheme goes 1, 2, 3, 4, 5, 6. At position number 1, we know we have a bromo group. And at position number 1, we can choose whether we throw the bromo group in an axial or in an equatorial position. If I put it axial, I'm going to have to put it on the face up because the arrow there is pointed up. That would mean that there would be a hydrogen going face down in the equatorial position. At number 2, for our methyl group, we know that the two groups have to be trans to one another. So now that I've placed my bromo in an axial position and it's face up on my ring, that means that my methyl group is going to have to be face down. Therefore, my methyl is going to have to be in an axial position as well, because I need it to be pointed on the down face of the ring so that it's opposite of my other group. Equilibrium arrows are used to represent the ring flips interchanging at room temperature. The more stable ring structure will be the one that's favored in the equilibrium position. So next let's draw a ring flip. Draw your parallel lines, opposite of how you initially drew them. And we have a series of parallel lines being connected. Position 1 is now right here. 2, 3, 4, 5, and 6 go around the ring. And what was axial becomes equatorial. So bromo was in the axial position. Now it's going to be in the equatorial position. But it's still going to be on the up face of the ring. Only equatorial points up right here now. Position number 2, methyl was pointed down. And we still want it to point down because we still want the two groups to be trans to one another, but it was axial. So now it will become equatorial. And the equatorial down position will be right here at number 2. So the up face and the down face do not change when you do a ring flip. Only axial becomes equatorial, or equatorial will become axial. So now analyzing our two structures for cyclohexane to determine the most stable conformation. And the one on the left, we have both of our groups in axial positions. So this one would be our least stable. And on the one on the right, we have both of our groups in equatorial positions. Therefore, this would be our most stable conformation. Sometimes we'll have a group in the axial and the equatorial position, and we'll have to decide which group would rather be equatorial. Usually the larger bulky group is going to want to be placed equatorial because that's going to be the one that has the most steric strain. Let's see how our chair conformations change when we switch the orientation to cis. So the molecule we're going to draw now is cis 1-bromo 2-methyl cyclohexane. If we just draw a quick flat cyclohexane ring to describe, we've got 1-bromo and we have 2-methyl, and we're going to put both of them on wedges because they're both pointing up or pointing down. They're both on the same face. Start with our cyclohexane chair. And we're going to have 1-bromo, and we can choose where we put the first one. We know they both have to be on the same face, but at 1 I'm going to put my bromo axial, and then 2-methyl. Now methyl has to be pointed up because I pointed my bromo up. So this means my methyl is now going to be equatorial. What would be pointed down would be a hydrogen in that position. So both of these are on the same face of the ring because they're both pointed in the upward position. Last time when we had trans, our methyl was in an axial position pointed down, so it could have been in an opposite face. Now let's draw a ring flip. And at position number 1, we're going to have our bromo group. And it was axial, so now it's going to be equatorial, but it will still be pointed up. So here's where bromo is now in the equatorial position. At position number 2, we're going to put our methyl group, but it was equatorial, so now it's going to become axial. So our methyl group will be pointed up. So the ring flip didn't change that. They're both pointed up still, but now they've switched positions. Axial became equatorial and equatorial became axial. Now we have to decide, would we rather have bromo in an axial position or would we rather have methyl in an axial position? And this will tell us which one is more stable. Bromo is an atom, whereas methyl is a carbon with 3 hydrogens coming off of it. Therefore, if I'm comparing the two of them, I would say that my methyl group is larger or more bulky than our bromo group. Since that's the larger group, I would rather place that in an equatorial position so it doesn't undergo 1,3 diaxial interactions. Therefore, the structure on the left where methyl is equatorial is going to be my most stable chair conformation. That means that 95% of the time it's going to be in this conformation at room temperature, except for the little bit where it undergoes the ring flip and looks like the structure on the right. Here our example molecule is trans 1-chloro-3-ethyl cyclohexane. First, let's draw it as a flat cyclohexane ring. At position 1, we have a chloro group, and now we have position number 3. We're going to have to put our ethyl group on a dash because I put my chloro group on a wedge, and we were told the orientation is trans. So our positions that we can have for our disubstituted cyclohexane ring can be 1-2, 1-3, or 1-4. And here we're going to do an example of 1-3 positions. So we're going to draw our chair conformation first. And at position number 1, I'm going to put my chloro group, and I'm just going to choose to put it in the axial position. That was my choice where I put it first. And then at position 3, since my chloro group is pointed up, how I drew it, I'm going to need to put my ethyl group on the down face. So here was 1, 2, 3, and if I put my ethyl axial, it'll be pointed up. So my ethyl is going to have to be in the equatorial position, pointed down. And we can use our abbreviation ET for ethyl. Next, we draw our ring flip for our cyclohexane ring. Maybe draw that part. Our chloro was axial, and here's position 1, 2, 3. It'll now become equatorial. It'll still be pointed up. So now the equatorial position is in the up face. And at position number 3, my ethyl was equatorial, and now it'll be axial, and because it has to be on the down face. So this position is pointed down. And notice you have a down arrow point there, so that means that axial goes down at that spot. So in our first ring structure, we had our chloroaxial and our ethyl equatorial. And in our second ring structure, we had our chloroequatorial and our larger ethyl group axial. So ethyl, you have to remember, is going to have a carbon with 2 hydrogens coming off and another carbon with 3 hydrogens coming off at the end. So this is quite larger and bulkier than just a chloro atom. So we're going to want to put our ethyl in the equatorial position. Therefore, the structure on the left is going to be our most stable cyclohexane ring. Lastly, let's look at an example where we have groups in the 1-4 positions. So we're going to draw cis 1-fluoro-4-methyl cyclohexane. So we're going to have position number 1, a fluoro group, and position number 4, a methyl group. And I drew them both on wedges to represent that they are both pointed up or down, or they're in the cis orientation. So first, let's draw our chair conformation. I always start with position number 1 in the axial position pointed up, but it's up to you. So I drew my fluoro on the up face here, and it had to be axial. So this is 1, 2, 3, 4. And our methyl group is also going to be pointed up because it's cis. So at position number 4, axial would be down and equatorial would be up for our methyl group. So both of them are in the up face. We're going to draw our ring flip. And here's position 1, 2, 3, 4. Fluoro was axial. Now it will be equatorial. So pointed up from the ring, we have fluoro here. Methyl was equatorial, and now it will be axial. So position 4, we have a pointed up where the 2 arrows connect. So we're going to have methyl going upwards in the axial position. And so they're still both on the same face, so it's still cis what we drew. In all orientations of the ring, we drew it cis. In the one on the left, we have our larger methyl group in the equatorial position. Therefore, this cyclohexane ring will be our most stable because we have less 1,3 diaxial interactions with our bulkier group.